Hello, I'm George Carlos and I'm a PhD candidate at VU Amsterdam. I will present the paper Fault-Tolerant Termination Detection with Safra's Algorithm. This is a joint work with Professor Van Valking from VU Amsterdam and Per Fuchs from TU Munich. So we want to detect the completion of a distributed computation. This is not trivial because no process has an up-to-date view on the global state, so we need a protocol. Termination detection is used in workable systems when tasks are created dynamically, and is required by other algorithms in order to function properly. Termination can be detected by a snapshot algorithm such as Chanty-Lamport, but this is a costly solution, so specialized algorithms exist. One of them is Safra's algorithm. Compared to others, it has a low cost in time and messages and no requirement for FIFO channels or acknowledgements. But before we discuss any algorithm, we must provide some definitions and a system model. The distributed computation whose termination we detect is the basic algorithm, and the termination detection algorithm is the control algorithm. The associated messages are called basic and control messages. There are n processes that communicate asynchronously through message passing. There is no global clock or shared memory. Messages arrive in any order and arbitrary but finite delays are allowed. A process is either active or passive. A passive process is only activated by an incoming basic message. In this model, we have termination when all processes are passive and no basic messages are in transit. So let's start with a fault-sensitive algorithm. Note that this is based on an optimized version from the Mirbas and Aurora with some modifications and optimizations of our own. The processes are organized in a logical ring. Each process counts the basic messages it exchanges and the token circulates the ring, accumulating these counts. When a process holds a token, it can detect termination or forward it. Intuitively, for termination, we want the accumulation to be zero, meaning there are no messages in flight. However, this on its own is not enough. On the left, J becomes passive and forwards the token. K is active and sends a message to I, and I responds with a message to K. Now at K, these counts cancel out, so if the accumulation is zero when the token visits, then detection would be incorrect because I is active. Another case is on the right. P and Q exchange messages, and again the counts cancel out at P, so detection at P is incorrect because Q is active. Both cases can happen if there is at least one message for which only the receipt is recorded by the token. In both cases, we say that the count is inconsistent. So we need to detect these two, and for the first, we must allow the token to revisit the sender in the next round. For the second, we must allow it to get past the receiver in this round. So we use a sequence number at each process to separate visited and unvisited. This is incremented when the token is forwarded and is attached to every message. When a message is received, if the sender has a higher sequence number but a lower ID, we know it's the first case. If the sequence numbers are the same but the sender's ID is higher, we know it's the second. If either holds, the receiver marks the sender as black, and the black colors are accumulated by the token. This forces a delay in detection until the sender is visited. Intuitively, when I marks J, it knows that the count of J is needed to reach consistency. The black accumulation in the token just keeps track of the furthest process whose count is needed. The algorithm has three parts. When the message is sent, the count is incremented and the sequence number is attached. When a message is received, the count is decremented and the receiver checks for a consistency violation. The left condition catches the first case and the right condition the second. If either is true, then black is set to the maximum of the previous value and the sender. This max function simply computes the furthest from I among its arguments. When I receives the token, it holds it until it becomes passive. Then the local count is accumulated and the local block is also updated with the new information from the token. If after the update I is allowed to check for termination, then if the accumulation is zero, I announces. Otherwise, it updates the black field in the token so that the later process can try to announce, and then it forwards it. So let's look at an example. Initially, all counts of sequence numbers are zero, and each process has black in itself. 0 sends a message to 2. It becomes passive and forwards the token with a count of 1. The token's black field is set to 3. This is a special case to make sure that each process is visited at least once. Meanwhile, 2 receives a message from 0. There is no consistency violation because the sending was recorded, so 2 only decrements its count. 1 receives the token, but it has only been passive, so just forwards it. While the token is traveling, 2 sends a message to 1. This message cannot violate the consistency because it has a lower sequence number. 2 receives the token, becomes passive, and adds it to its count. Since that was 0, the token is unchanged. Now 1 gets activated from the message from 2 and does a broadcast. At 0, we have a case of the second violation, so 0 sets black to 1. At 2, there is only a count decrement. At 3, we have a case of the first violation because the message came from the visited region, so 3 also sets black to 1. So far, the token knows it has to travel until 3, but both 3 and 0 know it has to travel until 1. And so it does, and when it visits 1, 1 checks for termination. But it cannot announce because the total count is not 0, so it lets successor try by setting the token's black to 2. Finally, at 2, the total count is 0, and 2 announces termination. So next, we will add fault tolerance to this algorithm, but first we need to refine our system model. All previous assumptions hold, and now processes are allowed to crash, but they cannot recover. Moreover, there are no Byzantine faults. Channels must be reliable, and it should be possible to establish a channel between each pair at all times. This is needed in order to avoid network partitioning. Unavoidably, we require the existence of a perfect failure detector. This is a local module at each process that monitors the status of other processes. Unfortunately, in a fully asynchronous setting, such a detector cannot be built. So in order to build one, we can assume an upper bound on network latency and have processes exchange heartbeat messages. If a process fails to respond within that bound, then it is regarded crashed. So we do introduce some synchrony, but it is hidden behind the detector's asynchronous interface. In this new model, termination is achieved when all alive processes are passive and for all messages in transit, either the sender or the receiver has crashed. There are 3 main ideas behind our transformation. First, messages to and from crashed processes are ignored. This means that the process may have to discard part of its count retroactively when it learns of a crash. But since we are using an integer to count, this is currently not possible. For this reason, we turn the local count into an array. This way, exchanges with other processes can't be counted separately. We must also discard the contribution of a crashed process from the token's count. So we make it an array as well, and each process writes its count on its own slot. So now, the count of a process is given by the sum of its array, and the accumulated count is given by the sum of the token's array. When a process crashes, the ring must be reconstructed. Also, the token can be lost during the crash. For this reason, we have a chain of responsibility with each process being responsible for its successor. When that crashes, the process sends out a copy of the last token forwarded as backup. After the crash, a process must update its successor to the next alive process it knows. But if the token was not lost, then there are multiple tokens circulating now. For this reason, we use a sequence number in the token, which is incremented when a new round is started. This way, duplicates are discarded because the receiver expects a higher sequence number. In order to accumulate the correct counts, the alive processes must agree on who has crashed. Also note that in our algorithm, it suffices that the failure detector of a process only monitors its successor and predecessor instead of everybody. This means that the process may only know of a subset of the crashes. So first, we use a set crash t in the token. This is where the local crashes are accumulated. Crashes are kept locally in 2 sets. The set crash I holds all crashes that I knows except those that I itself detected in this round. These are stored in the report set. This distinction allows for crash t to be kept at minimal size, and we will see how in a bit. Finally, if there are new crashes in this round, the token is forced to make another round so that everybody is informed. The algorithm has 4 parts, but I will only show 2 here. I have omitted the sending and receiving of basic messages. These are the same as before, with the addition that if a message is to or from a crashed process, then it is dropped. When a process learns of a new crash from its failure detector, it adds it to its report set. And then, if it happens to be its successor, it computes a new one, puts all the crashes in the backup token, and sets the token's block to itself so that it visits everybody else. Incoming tokens must have the right sequence number. If so, the process waits to become passive like before. Next, crust I is removed from crust T. Because the token made it back to I, everybody has learned this set. The token may have accumulated crushes that I doesn't know about. These are added to crust I. If some of I's new crushes are already in the token, they are removed from its report set. Next, I accumulates its counts to the appropriate index in the token. Note that only the crust I set is excluded from the sum. That is because if there are crushes in the report set, they will be accounted for after everybody else learns about them. If I is allowed to check for termination, it sums up the tokens array, again ignoring crust I. And if the result is 0, it announces. If it doesn't announce, if it has new crushes to report, it puts them in the token. It also adds them to its crush set in preparation for the next round. Then it clears the report set and forces the token to make another round. If it doesn't have new crushes to report, it sets the black color of the token, like before, so that maybe its successor can try. So let's illustrate this with a similar example as before. Initially, all counts are 0, and all sets are empty. 0 sends a message to 2, increments index 2, and sends out a token with a count of 1 at index 0. The token's block is 3 again, so that everybody is visited. 2 receives the message from 0 and decrements index 0. 1 receives the token, but it just forwards it. And 2 sends a message to 1 and 3. Both messages are received without violation, so 1 and 3 only decrement their index 2. 3 becomes passive and 1 broadcasts a message. But now 2 crashes. So both the token and the message are now lost. The other messages are received correctly, but both violate the count consistency of both, so both the receivers set black to 1. The failure detector of 3 detects the crash, but 3 is not responsible for 2, so it only puts 2 in its report set. 1 also finds out, and since it is responsible for 2, it sends out a token with 2 in its set. The token's block is 1 to make sure that everybody learns of the crash. Also note that from now on, both 1 and 3 will ignore the counts of 2. Next, the token is received at 3. 3 clears its report set, writes its count, and increments the sequence number of the token. That's because it is the last process in the ring. Meanwhile, 0, that is active from the broadcast earlier, sends a message to 3. The message is received without violation, so 2 just decrements index 0. 0 now receives the token and learns of the crash, but it does not put it in the report set because it didn't find out itself. Next, 1 receives the token, which has now made a full round since the crash was detected, so 1 can finally remove 2 from its report set and check for termination. But the sum is not 0, so 1 forwards the token to 3. 3 receives it and writes a -2 to it, which makes the total sum 0, so 3 announces. So that was our fault-tolerant algorithm, but what is the cost of it? The main one is the linear increase in the size of the token compared to the fault-sensitive algorithm. This could limit scalability. On the other hand, the impact is reduced by the fact that we do not send many tokens anyway, because only passive processes forward the token. Also, if we assume stable storage, we can have constant size again. When the crash is detected, the token travels an extra round. This can increase the detection delay. On the positive side, if multiple crashes happen in the same round, the extra rounds overlap. Finally, we have the cost of the failure detector. This is mandatory in all fault-tolerant algorithms. Our algorithm can work with heartbeats only from successor and predecessor of a process. So we can have less messages, but potentially at the cost of slower convergence. So there is a trade-off here. To test our algorithm, we first built an emulator. For active processes, we choose a random number of actions to perform. And for each action, we flip a coin to determine if it will be a computation or a basic message. For a basic message, we invoke the receive part of the algorithm after some random time to emulate latency. Which processes will crash and when were also chosen at random. For the random choices, we used two probability distributions. We also applied our algorithm on top of Chandy-Misra rounding algorithm and the Affek-Kuten-Yang self-stabilizing spanning tree algorithm, as both of them require termination detection. We ran these implementations on the DATS5 cluster at VU Amsterdam. Now onto some results. Here we measure the tokens in runs without failures. On the left we have the results of the emulator and on the right the others. In the top part we see that in both cases the fault-tolerant algorithm requires the same number of control messages as the fault-sensitive algorithm. In the bottom part we see that termination is always detected within one round. Next we have the tokens on runs with failures. On the left only 1 to 5 processes fail and on the right 90% fail. The total number of tokens in both cases is roughly equal, which implies that there is actually an increase because we have less alive processes, so they must be exchanging more tokens. When more processes fail, the ratios between before and after termination are actually different. The reason is that the emulated basic algorithm does not compensate for crashes, but in a real situation this is something we would expect. And this is what we see in the plot. For the emulator, the tokens before termination stay roughly the same. But for the other runs, we see a big increase. That is because these basic algorithms do take extra steps after a crash. This implies that the characteristics of the basic algorithm are important to the performance. So to conclude, I have presented a fault-tolerant variant of Safra's termination detection algorithm. The algorithm imposes a linear increase in the size of the token. Future work could investigate the usage of stable storage so that the token size can go back to constant. Our algorithm forces the token to travel an extra round for its detected failure, but these extra rounds can overlap. Finally, our algorithm can tolerate n-1 failures and it does not impose any message overhead in the absence of failures. If you would like to learn more, feel free to check our paper and the code on GitHub. And feel free to contact us with any questions. Thank you.